So the encrypted economy has had two podcast episodes focused on blockchain interoperability solutions. With this one, rather than focus on a primary architecture, I thought we would take a step back and talk about different considerations that a distributed network needs to contemplate as it relates to interoperability. And I was lucky. Raphael Belchior, a PhD student who currently works for Blockdaemon, recently published a paper on this very topic. It's complete with diagrams and a decision tree. We all like pictures, don't we? I took some time at the beginning to set the stage and also to explore what a new entrant in the space like Layer Zero, as well, compare and contrast to IBC, does before getting into specific considerations. So I look forward to bringing this episode to you. Separately, podcasting takes on a lot of time and has an opportunity cost. With that said, I love engaging with the guests and sharing with the community. But for the next few weeks, I'm going to be doing my episodes every other week. Hey, this is my 79th week of straight weekly podcasts. I'm still committed to delivering both challenging and engaging content to the encrypted economy. Please stay tuned. With that, I bring you the episode with Raphael Belchior. Welcome to the Encrypted Economy, a weekly podcast featuring discussions exploring the business, laws, regulation, security, and technologies relating to digital assets and data. I am Eric Hess, founder of Hess Legal Counsel. I've spent decades representing regulated exchanges, broker-dealers, investment advisors, and all manner of fintech companies for all things touching electronic trading with a focus on new and developing technologies. All right. So today we are joined by Raphael Belchior. He wrote a article that I picked up. He's also worked with Thomas Harjano, but his article is, "Do you need a distributed ledger technology interoperability solution?" Now, Raphael, first of all, welcome. Before I go too deep into it, thanks for joining.
Thanks a lot, Eric. Nice to be here.
Now he's in Lisbon, which is becoming sort of like a European capital of sorts for crypto. I know the Solana conference was there, but I have even clients that are based in Portugal. So certainly a lot going on there, and a great place to sort of keep an eye on and also visit. You can't go wrong visiting Portugal, that's for sure. So you wrote this paper, "Do you need a distributed ledger interoperability solution?" Now, I want to hear about your background, but I'm just sort of lining up as to, how we got to where we are today. So, we've talked a lot about interoperability on the podcast, trying to sort of flesh out, how it works. We had Wanchain, we had Jack Liu and Weijia Zhang from Wanchain on. We had Thomas Harjano on as well. And so, now we're through you, we're going to take a step back and try to figure out, sort of do an ontology. I don't know, but we're going to break it into buckets and try to get a better understanding of the different types of solutions and where somebody actually needs it. But we get ahead of ourselves, which is what I usually do. So first, let's go with your, let's learn a little bit about your background and what motivated you to write this paper.
Thanks a lot. I think we have a lot of ground to cover, so let's try to keep it efficient. There's really a lot to talk about. I come from a distributed systems security background, and now I'm doing my PhD specifically focusing on blockchain interoperability. So that's sort of how it started. And currently I'm employed at Blockdaemon, which is an infrastructure provider. So we basically offer different nodes across lots of different protocols. So naturally, there's a tendency to enter the cross-chain space. We started our research by writing a paper called "A Survey on Blockchain Interoperability, Past, Current, and Future Trends," which is a systematic literature review. So a systematic literature review aims to collect all the present, as more as possible, right, knowledge on a certain research area and try to dissect it into structured knowledge. So we basically conducted this review by going to Google Scholar, writing our search keys, which were basically blockchain interoperability, cross-chain, interledger approaches, and we got back around 400 documents. Those documents were white papers, academic papers, blog posts, presentations, well, from different sources and from different people who wrote them had different backgrounds. We read their abstracts, their titles, and we tried to understand which ones would be useful to answer three main research questions. So those questions were, what's the current status of blockchain interoperability? So what's the current available solutions in the market and also in the academia? Are the technical requirements to enable blockchain interoperability currently satisfied? So can we actually build those types of solutions reliably? And finally, are there any use cases that benefit from a multi-ledger cross-chain approach? Those were the three research questions we tried to tackle in this first paper. So from those 400 documents, we figured out that about 100 were useful. So we read them and we studied them and we dissect them. And as you can figure, that took a long time. So by the time the article is written, it's already outdated, but I think it's, well, a difficult thing to tackle in our field because blockchain is going very fast. But we did a paper and we realized that yes, that it is possible to build blockchain interoperability solutions. There are different types. So there's an ontology that can place them in different buckets. And finally, there are some interesting use cases that are born out of this complexity. Yeah, so that paper is very useful because it also provided us a lot of research directions, which we found three to be the most important ones. And those research directions also gave birth to this paper that we're going to discuss today.
Do you think the European interoperability framework would be useful to talk about as a mental model, or do you think maybe we just dive right into the classifications? You tell me.
I think it's better if we briefly discuss this framework. So, because it gives us an idea on what different aspects of interoperability we can talk about. So this is one of the more concise frameworks I found. It divides interoperability in four layers: synthetic or technical, semantic, organizational, and legal. So while our expertise tends to fall into the first two, the later are the ones that can possibly provide the highest degree of maturation to the technology. So the synthetic layer tries to define data formats which your interoperability protocols could use. So it's about the bits that are transferred from one place to the other. The semantic layer attributes meaning to those bits. So actually a cross-chain message is nothing but a payload. The semantic layer takes that payload and transforms it into information that's useful and that can be used in the blockchain. Then you have the organizational layer, which typically is discussed more in the business process management research area and also a bit of software engineering, but it defines what are the processes behind or the agreements, the deals that can be made between organizations that want to interoperate. And finally, you have the legal layer. How can you have a system that interoperates across legislations and different regulations, which is also a bit of the work that we've been doing at the ODAP group at the Internet Engineering Task Force.
Excellent. So let's talk a little bit about trustlessness. When does it make sense for an interoperability solution not to be trustless, but to be trust-based?
Right. So there's a famous dilemma or trilemma, should we call it, on blockchain, which is there is always a trade-off between decentralization, security, and scalability. And I think this can be applied to interoperability as well. There are no completely trustless interoperability solutions because, well, more or less, we can talk a bit about it later. Because for blockchains that do not interoperate natively with each other, such as Polkadot, because it's actually a sort of sharded blockchain where each sub-blockchain or parachain can natively interoperate with each other, meaning that there is a standard communication protocol that each one can use. And actually, the relay chain is nothing else but a blockchain that mediates cross-chain communication. So actually, the trust assumption is that the relay chain will not misbehave because it's very decentralized and the actors have different incentives. So that's the characteristic that raises decentralization and security of the interoperability solution, but at the expense of scalability, at least so far. And then on the other hand, you have more centralized solutions. So what you can have between two blockchains to make the interoperation ends up being a consortium or different consortia even, where the one of the spectrum, the end of the spectrum is a whole blockchain to do that mediation, or a single party, right? Or a smaller subset than a blockchain. And a single party can also be adequate for certain use cases, which is, for example, enterprise-grade blockchain interoperability, where you want these parties that do the interoperation, we call them gateways. They are identified, they have legal tender or legal status. For example, they are operated by a virtual asset service provider. And so, whereas we can place our trust on that entity because it's acting in a permission environment. When that's the case, when our security model is that, we can opt by a more centralized solution and have more efficiency versus the amount of decentralization other options offer. It depends on the use case.
Right. Well, we'll be getting into that. And then I guess let's start to talk about the different classifications of interoperability solutions and start to break that down a bit. So you wrote the papers, so why don't you walk us through it?
Right. So some of the background that we might want to cover a bit before we dive a bit deeper. It's very simple. It's the notion of DLT protocol, subnetwork, and also network. So DLT protocol is the algorithms, the procedure, the set of procedures that blockchain nodes need to implement to create a DLT network. So the DLT network is a set of nodes that implement the DLT protocol and are connected to other nodes that run that protocol. So for example, the Ethereum mainnet, a private Ethereum network, a network on Hyperledger Fabric, and so on. And then we have subnetworks, which are partitions of that original network that can have different functionality or enhanced functionality. So for example, in Hyperledger Fabric, there would be the channels. In Polkadot, we would have the parachains. In Ethereum, we consider the mainnet, the testnets to be their own subnetwork. So the network is equal to the subnetwork on that case. And following this type of division, we thought that there are really only two types of interoperability solutions. The ones we call oracles and cross authentication. This approach is tries to make it very simple, so telling people how does the interoperation happen, and not what is involved in the interoperation. So if you want to answer the what, we can look at our survey, our first survey. If you want to look at the how, we can look at the survey. So for example, the very well-known bridges, oracles, roll-ups, etc., we consider them to be design patterns that one can implement on top of these solution types. Okay, so the first solution type are the oracles. The idea is that you have a set of parties capturing information from a source chain and transmitting it to a target chain or DLT, and they can run arbitrary protocols in between. So you can have a vanilla oracle like Chainlink. You can have a bridge, because the bridging mechanism occurs basically by having a pair of smart contracts and a set of parties that redirect proofs to the other smart contract. So you end up having a combination of relayers and the smart contracts, which we call the bridge typically. They come with its own security assumptions and security model, but underlying the technical basis, it's very simple. There are parties in between making a transfer of information that is interpreted in different ways. Okay, and then you have the cross authentication where this doesn't happen. Cross authentication comes with the so-called hashtime lock contracts. So essentially, when you want to do a cross-chain asset transfer, you're really not doing to be, if you want to be rigorous, you're not doing any cross-chain transfer, because what you're doing is a pair of transfers on each chain. All right, but the abstraction of that could be a cross-chain transfer. And that's typically very native, because you don't need any functionality than what the current blockchains currently offer. You just need to make sure that the signatures to create a hash lock are compatible on both chains. So you can create this communication channel. It can even be off chain, where I promise to give you some token on blockchain A for some token on blockchain B, a pair of smart contracts with a secret can do the trick. I can talk a bit more in detail about this.
Sure. Maybe you could take a couple of solutions like layer 0 and take a step back. And as we think through these things, like how do these type of interoperability solutions fit in?
All right. Yeah, I think that's a great approach. Layer 0 appears to be an interoperability solution that conceptually is not very far from IBC. Okay. So IBC works by having,
which is the Cosmos ecosystem, right? So, yep.
Yes, it's used by the Cosmos ecosystem. So the Cosmos powered IBC hubs are compatible with other fast finality blockchains, but IBC can be used in more blockchains. Pretty much all the blockchains that support having a live client. But yeah, so IBC work. All of these types of solutions at the end of the day are very similar. What differs is the security assumptions, the smart contracts, and the smart contracts here, there is a gigantic variability, and with it security risks, as we have seen so much. But basically, IBC has a set of light clients on the blockchains to interoperate, which are on-chain, so smart contracts that can verify state happening in other blockchains, and a set of relayers that pass those proofs to be verified on-chain. You can verify state that happen on other blockchains via Merkle proofs, for example. So the idea is that you have block headers, okay, and you provide a Merkle proof against that block header, which is basically a part of the Merkle proof along with some data, a transaction, so you can prove that that transaction is included on the block header. And this is typically secure. In specific with Ethereum 2, you'll be able to build a lot more trustless light clients, because there is a sync committee that signs the beacon chain state. And when you're receiving the Merkle proof, the Merkle tree referring to that beacon state, you have the validators from the sync committee signing that information. So you can actually see that if that tree is signed by the Ethereum validators, by that committee, then it must be legit.
Okay, so I think then as we go through this, like because I think IBC and Layer 0 are capturing a lot of attention now in the interoperability space, and it's as we go through your buckets, and you know the Oracle-based solution, the asset transfer commit solutions. Let's let's talk about IVC and layer 0, but toward the tail end of each one of those, just so we get a sense of how they fit in. Certainly, the Cosmos ecosystem has gotten a lot of attention as of late because of its interoperability in ways that I think a lot of the other chains do not, and the ways that it facilitates developers programming to it. But maybe we get a little ahead of ourselves. That's my trademark. So why don't we start with the framework, the Oracle-based solution and the asset transfer commit framework that you talked about in your paper, and then start to figure out how these work across the various ecosystems.
Right. Yeah. Good. So oracles. We identified two types of oracles. First, we have the push-based oracles, and then we have the pull-based oracles. There's a figure on the paper, which is figure 10, that explains this process in a very visual way, so it might be good to take a look. But essentially, the pull-based oracles are the ones that are possible to implement in order, validate, execute blockchains like Ethereum. So if you want to make, for example, an HTTP call on-chain from within the Ethereum network, you need to use an Oracle network, such as Chainlink. You basically issue that request, making a transaction against the Ethereum network, and then the Chainlink Oracle network will parse for those requests, for those transactions. When it sees that there is a request for a certain piece of information, for example, on the GET HTTP request, it fetches the information, right, and it returns it to the network via another transaction, right? So this type of oracles require two transactions because you need to make the request for the data and then use that data. Okay, this is one of the ways you could use Chainlink. On the other hand, you could use also push-based oracles. So Chainlink also provides smart contracts that are being consistently updated for different types of information, and you can ask that information on chain with one transaction. Okay, so Chainlink also has a good range where you can a good range of ways for you to ask information. Okay, but you have another type of pool-based oracle which follows the execute, order, validate model, which is used in Hyperledger Fabric, a private permission blockchain, where you can make on-chain HTTP requests directly on the smart contract itself. So Hyperledger Fabric uses the smart contracts called chain code in Hyperledger's jargon. Can have you can use arbitrary libraries and code there, including libraries that allow you to make some HTTP requests. And it works due to the nature of how transactions are processed within the Hyperledger's Fabric ecosystem. Okay, so in Hyperledger Fabric, when you want to make a transaction, when you want to issue a transaction, you sign the transaction, you send it to some entities called the endorsing peers. Those endorsing peers execute the transaction into an isolated environment. So, for example, making an HTTP call, and then you collect those results. Each of the proposals to each of the endorsers have what is called a read-write set, where it has the result of the computation they did, basically, and you give them to the orderer service. The orderer service validates that information, so if the timestamps are okay, if the responses are the same, and so on, and then it sends them to the committing peers. The key insight is that if the read-write set is the same, so if the result from the HTTP requests are the same, then the transaction can go through. Otherwise, if they are different, it won't go through. So you can you can have a decentralized way of obtaining information from the exterior within these private blockchains, as long as the results within a certain time frame are the same.
Now, so today, what would be a key example of an Oracle-based solution? I mean, obviously, leveraging Chainlink would be part of it, but what are some of the solutions that actually actively deploy like an Oracle-based mechanism for interoperability?
So, for example, any bridge, we can look at bridges as being design patterns built on top of oracles. Every bridge has a set of operators that are verifying state in one chain and recreating state on another. So typically locking tokens and unlocking tokens on other blockchains. And you can build a lot of different infrastructure and business logic on top of these oracles. So all the bridges would be an example of solutions based on oracles, the oracle networks, relayers, and so on. So most of the interoperability solutions are based on
Oh,
oracles.
okay. And where does layer 0 fall in IBC? Are they Oracle based?
Yeah. So I would say they're very similar. They would be oracle based. I haven't seen the details on layer 0 documentation and white papers on how do they, for example, allow a user to only pay fees once for a cross-chain transfer, because there is no escape. You need two transactions. You need a locking transaction and an unlocking transaction, unless it's within an ecosystem where you have interoperability natively, like a transaction between parachains. But between heterogeneous blockchains, as we call them, so Ethereum and Polkadot, Fabric and Cosmos, etc., I don't see that there's an escape unless the cost is absorbed by the operators. So conceptually, I think IBC and Layer 0 are not very different. Layer 0 has some more logic, more abstractions built on top of that oracle. So, for example, the unified liquidity pool. IBC focuses on the core infrastructure. It's more on the synthetic layer. Layer 0 is more the semantic layer.
So layer 0 has, from my understanding, has pitched itself as being sort of effectively, hey, we'll handle the interoperability, the messaging component of interoperability. We'll take that component, and you just worry about building your systems and connecting, but we'll do that messaging layer. Is that really good marketing, or is there something that's very different from how other interoperability solutions pitch their product?
Right. Yeah. If we look at that perspective, they provide synthetic or technical interoperability. But it's more than that, right? Because if they want to absorb the complexity for the end user, which is what they're trying to do, it's a very good thing to do. Because if you want to manage all the complexity as an end user, it's very difficult, right? If I have some tokens on Ethereum and I have no Ether, it's a complication to obtain other tokens. So if they provide those abstractions, they would be actually participating on the semantic layer, and they want to provide a similar messaging structure that IBC also provides, right? But they have this way of hiding complexity from the end user that IBC does not have. So with IBC, you need to create your own bridges, you need to create your own oracles, you need to create your own business logic. Whereas Layer 0 seems to be aiming at providing that out of the box, which is probably a very good thing. So open source projects like Hyperledger Cactus, which I'm a collaborator, also provide this type of infrastructure. So you have a Cactus node, which is basically a modular construct where you can plug in different functionalities. So imagine the Ethereum connector and then the Polkadot connector and then a bridge plugin. So you can have infrastructure for creating a bridge between Ethereum and Polkadot, right? And Layer 0 already provides some of those pieces for you to glue things more easily.
All right. So while we're on the topic and on Layer 0, how does that impact the trifecta? what are you? What assumptions? What's being sacrificed in the process? Is it because there's always a trade-off. I should say, as opposed to the sacrifice, a trade-off. It sounds to me like possibly layer zero uh, moves away from a decentralized because now there's a higher degree of trust on layer zero to the extent you abstract it away. Duh, right? That's kind of obvious. You can't have your cake and eat it too. There theoretically could be some security concerns with that, although it's really dependent of how they handle it. Somebody has to handle security, and so the question is where and how. But what do you see as some of the are those the trade-offs that you encounter with the solution like layer zero? And if they pull it off, like, and they handle centralization, what I again maybe I'm off, but they handle centralization, they handle the security issues well, then people maybe don't care, and it becomes like another Infura or another centralization point that has a lot of has some risk, but to the extent they manage it well, it's they'll get their ready consumers.
That's a very good question. I think there's always a trade-off. And assuming that layer zero wants to fix the decentralization variable, so keeping it as a core value of their product, then the trade-off is between security and throughput or scalability. So I think typically when these projects take off, they always end up sacrificing decentralization at first. So they have centralized operators because it's a very easier solution to build. And later on, they replace those centralized operators by a blockchain or a network of operators. And if layer zero does this well, then I think things will converge to a more centralized approach because the end users will have the usability and the ease of use and the simplicity as a good trade-off for decentralization. That's what's happening basically in where you have big node providers providing your infrastructure. You could argue it's towards centralization, but at the same time, if those companies are obliged to provide faithful services, then you just have the infrastructure, and it's not decentralized. You just have the infrastructure, and you can use it. Yeah.
Right. So your paper makes a distinction between a permanent asset exchange and a temporary asset exchange. It sounds like the temporary asset exchange probably typifies like an asset transfer commit execute protocol, but and maybe a permanent asset exchange is maybe more aligned with Oracle based, but maybe you could explain that a little bit more.
In our mental model, we define that the object of interoperation can be data or assets. So we have data transfers, asset transfers, and then asset exchanges. Asset exchanges occur when you have a set of transactions happening in a set of blockchains that realize an asset transfer without those transactions happening in between. So they're native transactions. So asset exchanges are just terminology for the cross authentication type of solution to realize cross-chain asset transfers. A permanent asset exchange is what typically happens when you deploy a hashtime lock contract. A pair of transactions happen, assuming it goes within the defined limits, time limits, and each party receives its asset. Whereas a temporary asset exchange would correspond or implement a type of cross-chain flash loan, okay, where you have to return the assets you borrowed, not in the same transaction, but in the set of transactions that correspond to the asset exchange.
And would that also be for like when you have like hash locking on both sides of the transaction for cross-chain coins, cross-chain token? Because presumably at some point you're going to unlock, there's going to be an exchange back, although
Right. So the hash log the hash logs can implement a type of escrow where you can also lock your coins as collateral for some operation. Right. So in a cross-chain setting, you can have one transaction locking your collateral and another transaction performing some computation. And after some time rounds, if the if the unlocking condition is satisfied, that hash log can be open. So precisely, that's the point.
I also wanted to touch on the connection modes for interoperability, things like the nodes, proxy, gateway. If you could kind of break those down and explain how they fit into the different models.
Right. Yeah. So the connection modes are essentially how can blockchain interoperability solutions, and not only, connect to DLT networks. So the simplest is the DLT node. It's the software that implements the node. You can go to GitHub, you clone the project, you build the project, and you can run your node, Ethereum node, Polkadot node, etc. And you can not only contribute to the network, but realize operations on the network. So you can read the state, you can collect transactions and send transactions to the network, so mine, and so on. So when you're excuse me, when you're operating a blockchain interoperability solution, you necessarily need to read state and to write to state. So the most direct way to do that is you run your own node, and then you run your blockchain interoperability solution and you couple them, right? So if you want to read the network, you access through the node. However, there are lots of downsides to it. So it's expensive, it requires constant maintenance. You need to keep your nodes updated. In some situations where you are, for example, validating also with your node, if you have some downtime, you might be slashed. And so we have the DLT proxies that aim to solve this problem. So proxies such as Blockdaemon can host your nodes so that you only need to focus on running the interoperability solution. So with this, you can have higher throughputs, you can have some load balancing, you can even defer your validating, your staking to other nodes, although this would be more in the DLT gateway scene. And so you have a more reliable nodes that you can use to conduct your interoperability costs. Some time ago, I was talking about decentralization. So if everyone uses the same node provider, this tends to be tends the ecosystem to converge into a more centralized ecosystem. That's one of the perspectives, and that's why we have several competing providers that have different incentives and contrary opinions sometimes. But at the same time, if you do not have any technical expertise, if it's hard to configure a node, probably the best solution is for you to have your node hosted by a third party so that you can contribute to the network. And that raises the decentralization of the network. It's a bit paradoxical, but I think that hosting infrastructure is really at the core of any technology. So the more infrastructure you have to support the technology, the more mature it is.
Right.
And finally, we have the DLT gateways. So the gateways are collections of services that are built on top of nodes or on top of proxies. So for example, Block Explorer, Hyperledger Cactus running a certain protocol, Hyperledger Cactus node, such as ODAP, a node, a collection of services that, for example, implement cross-chain API like Blockdaemon's Ubiquity or Quant's over Ledger, and so on.
So the gateway is that the simplest?
It's the most complicated because it has the more abstractions built on top of it. But we can look at it as an isolated, as a logical unit that has node functionality and some services on top of it.
Okay.
So we could have, for example, when interoperability will be more standardized, we will have possibly the cryptocurrencies banks having to exchange assets with each other in a more structured way. So they could have, for example, a gateway running on secure, provable hardware that has only installed a DLT node or a connection to a proxy, and for example, the ODAP protocol or other protocol that implements asset transfers. So you could sell it or ship it in a box. It has a validator, it has some software on top, and it only aims to do that.
So is the gateway potentially a better solution if you're looking to establish sort of a private DLT network? Or is it not really a question of whether you're looking for your transactions to be all sort of within a closed private blockchain network or not? Is that not really a function of that?
If you're operating in a private network, you don't have many options. You either run a node or, well, you can actually run a DLT proxy if the node providers have access to the private blockchain, which doesn't happen all the time because it might be the node providers typically do not support private blockchains or gateways, which are nodes with some services running on top. So it comes to the trade-offs. Nodes are probably more difficult to deploy and to maintain, but you have direct control over them. Proxies and gateways, or gateways with proxies, not so much, but you're losing a bit of control there. So if you trust the node provider, it's fine. Otherwise, it's better if you just run your own node.
Right. Let's talk a little bit about hashtime locks and the different types of hashtime locks and how they work in an interoperability solution.
Right. So hashtime lock contracts were actually one of the first mechanisms to provide interoperability. I think back in shortly after Bitcoin was created, and it has two core constructs: the hash locks and the time locks. So a hash lock is basically a mechanism for you to lock state, where you basically create a hash out of a secret, and you publish that hash or you use that hash in a smart contract. So if there is a transaction that carries a payload, and the payload is the secret of the hash, such that the hashing returns the published hash, then we can create a transaction, or better, send some tokens to a certain recipient. Okay, so with this you can create a smart contract with a lock. Okay, that can be used as the first step to make this asset transfer. And then the secret is that on the other blockchain, you also create a smart contract which opens with the exact same lock. So if you provide the secret such that the hash is equal to the published hash, then it transfers some tokens. So what happens is that the first party has the secret and the second party doesn't have the secret. When the first party tries to unlock their assets with the secret, the second party will have that secret. So the second party can also use that secret on the first smart contract. So it's I have the key, I can unlock the lock, and then you'll have the key and you can unlock the first. And this has to be bounded in time. Otherwise, some attacks. There's the possibility that, for example, if the second party doesn't use their lock on time, they'll lose the funds. So only one transaction would have happened. And we need time, because otherwise we could have our assets locked indefinitely. So the rationale is, if the counterparty does not provide a secret within this time frame, probably they're not interested. and I have my liquidity here stuck, so we'll just cancel everything. So this mechanism is quite effective and well studied to make this type of transfers, but again, it has some drawbacks. All parties need to be online, checking for the transactions. There's sometimes a not so trivial trade-off between the amount of time and how fast you want your liquidity. Because if you set your time locks for too long, you'll have your liquidity possibly locked for a long time. Otherwise, it's easier for you to lose your assets, right? So some other alternatives have been studied in this context, and typically they involve oracles mediating that complexity. So you could, for example, lock your collateral into a specific account, and on the other blockchain you are minted some tokens according to that locking. And the lock, the account that receives your funds that acts as an escrow has some collateral locked, such that if they steal your funds, then you have the collateral.
Excellent. I thought table 2 in your paper, where you went through different considerations and which general category of Oracle or cross authentication to leverage. You want to kind of talk through that a little bit?
The paper presents a lot of background, everything that is related to interoperability solutions, so that at the end you can choose the proper interoperability solution given your use case. Okay, so this table tries to make that summary. It basically says that oracles typically use the gateways more than cross authentication mechanisms. Oracles can be used to build more general purpose use cases because they have more powerful infrastructure natively. They're not so easily implementable and also decentralizable. There's a lot of work behind decentralizing an Oracle network and making it efficient and secure. That's why we have several multi-million-dollar projects only to implement Oracle networks, right? But oracles end up allowing to build a lot of different use cases and design patterns on top of them, bridges, rollups, relayers, and they're really the source for interesting use cases. For example, two of them we are exploring are blockchain migration. So imagine that you have your decentralized app running on a certain blockchain. How do you, as automatically as possible, migrate the state of that blockchain, of that application running on that blockchain to another, right? You need some interoperability mechanisms here. You probably need evidence and proofs that the computation that is being transferred really occurred on the source blockchain and so on. So these are use cases that can be built directly on top of oracles. Cross authentication mostly aims to exchange assets between parties more or less directly, right? And so we end up having a bucket that's bigger than the other, okay? On our past survey, we kind of take that big bucket and partition it according to the design pattern. So it's perhaps easier to have a complete idea of each design pattern.
Okay. Down at the end of the paper, there's basically a couple of charts that I think is very helpful. They're known as figure 15. They're figure 15 in the paper and figure 16 in the paper that really gets into, it's a decision tree. So I encourage anybody who's listening, we're putting a link to the article in the show notes. So I encourage you to go to the paper itself, particularly for this part. But Raphael, if you could just walk us through sort of that decision tree in those figures.
Right. So this is, I would say, the main contribute of the paper. So after suffering for 20 or 25 pages, you finally have the promise that, okay, we're trying to help you to find out the solution. The reason that it takes some time, some effort to get here, it's because, in order for us to choose the correct solution, we need to be able to more or less, at least a bit, right, systematically comparing. And it's not possible without the background. And the construct we use to compare the solutions are the P levels and the C levels, and also some performance metrics which are used on the diagrams, right? So the P levels tell you how so can the system interoperate with others as it is. That's the P level. And we have 4 P levels, P level 1 to P4. P1, the interoperation system can interoperate across functionalities of the same network. P level 2 can interoperate across subnetworks. P level 3 across networks, and P level 4 across DLT networks of different DLT protocols. So you have it tells you basically how powerful the solution is, right? It's something like interoperating across, let's say, Polkadot's parachains is not the same as interoperating between Ethereum and Polkadot. There's a complexity increase from each P level. And that's because, when you're interoperating across heterogeneous blockchains, you also have the consensus, the different security models, and so on that complicate the process. And then you have the C levels. Basically, it tells you how compatible are the solutions in terms of the semantic layer, organizational layer, and legal layer. So it tells you if the interoperability solution can provide support not only for the semantic layer, but also for the organizational and legal layer. So in the future, you could have solutions that assure you that you're not doing anything illegal or that goes against the current regulations. Okay, so getting that out of the way, we can focus on figure 15, which basically helps you choosing a proxy, a gateway, or a node, and also if you should host it yourself or host it, have your solution hosted by a third party, right? So we start on the 1A label, and we make a series of very simple questions that give you a general direction. So if you're not connecting to at least one DLT, you don't need a DLT interoperability solution.
Hopefully,
right?
You're not even looking at the diagram at that point, but it's the base level question, right?
It's a base level question, but should be asked, right? This is similar to that famous paper, Do You Need a Blockchain? They also have a decision diagram, and they also start with the very simple questions. That's how you should do it, right? Then, are you connecting to just one DLT network? Well, if you're connecting to just one DLT network, you probably just need one DLT node. Perhaps you might need a DLT proxy if you need more like high availability and high, sort of guarantees that it won't go down, right? Then if you're connecting to multiple DLTs, if you need some cross-chain logic, more complex abstractions, you might need a DLT gateway, okay? And then the decision tree. So this is actually in the same figure, 2 decision trees. The second one is quite simple. If you want to have the hustle to administer and monitor your own nodes, you might self-host. So run your node. Otherwise, you can defer that job to a third party. So Infura, Blockdaemon, and others. That tells you how you should host your interoperability solution. Okay, and having that in mind, we can try to look onto the functionality that your interoperability solution should provide, right? So that's figure 16, right? So this figure tries to evaluate what type of what type of asset are you trying to interoperate, if it's data or pure assets, right? It asks you if you need to transfer data, if you need to transfer assets, if you need to exchange assets, right? And at the end, we try to divide the result, the path, right, by P levels and by C levels. Okay, so what we found is that the P level that's most impactful, let's say, it's P level 4, because the real difference between most of the interoperability solutions is that if they can interoperate across heterogeneous networks, that's P level 4 or not. So everything else goes one side, P level 4 goes the other. And then also we have the C levels, right? If C level 1 is enough, so the semantic layer is enough, for most solutions it would be, or if you need regulation and laws, if you need to take them into account. Okay, and now that we have most of the information, we go to table 4, which is on the next page, and we need to cross-check our P levels, our C levels, our interoperation mode, and it will yield the final output of the decision of these decisions.
That's going to be a little easier to follow if you're on the paper. So basically, it's a way of walking through the different hosting questions, the complexity, the types of data that you are looking to transfer, cross-chain interoperability. And again, these decision trees are extremely helpful, but they largely flow from the paper and some of the core considerations that we reference on this podcast. We covered a lot. What do you think maybe we should be touching on a little bit more?
That's a good question. There is a lot of work behind this type of papers, not only these, obviously, because there's a lot of complexity out there. This is a primer for people to have more or less the idea of what do they need, right? But then the specific implementations, it's another, I would say, another paper and another 3-hour conversation where we can choose the right design patterns. But there are several challenges that are not addressed yet by the industry and also the academia, which I would say are supporting tools for blockchain interoperability. So decentralized identity, modeling, analysis, visualization of cross-chain state. Only the formalization of what constitutes cross-chain state, so a set of transactions happening in several blockchains that create an abstraction. That's also not explored. So imagine this is something that we're currently working on. A cross-chain transaction can be admitted to be a set of transactions on different blockchains. And if you correlate them with an ID, okay, you can have a log, okay, of operations or transactions that correspond to a certain use case, a business use case. And it turns out that you can create a model, a formal model out of that log. So you can represent them with APCs or Petri nets or even BPMN. And if you have the formal model of what is supposed to happen, you can track in real time what's happening. So imagine you have a breach, right? You have a model of what's supposed to happen, and if there's an attack or there's some outlier behavior, you can know it in real time and act accordingly. So those type of projects and tools I think are very important for technology to settle in. Some more research on formalizing blockchain interoperability, and finally applications that can satisfy not only enterprises, so more centralized applications, but also the end user that wants maximum decentralization, right, in a secure way. And I think that's still very hard to do because bugs in smart contracts can cause the minted token to be stolen, and that's an issue that so far hasn't been addressed.
And which one of these, let's say that security trumps all else, What is the no-brainer solution that you have to explore? I know there's a dependency. It's a question of what, but let's say you're doing an asset transfer, and let's say that security is your primary consideration. Is it short of going all private with permission parties on the network? What solution do you think is going to attract the most interest?
Well, if security is paramount, we can have a very simple way of solving the problem. We take security and scalability, and we have a centralized party doing the interoperation for us. So, for example, centralized exchange. Although they are also hackable.
Right.
So, at the end of the day, if you have a very opaque system, it's in principle harder to break into. So it's more secure, or at least it doesn't have so many eyes onto the honeypot that it might have. That party can issue the transactions for you. It can give you the tokens for fiat and so on, and you have a way to do that very efficiently, right? So I think here that the more centralized things are, probably the more secure. Probably it's not a given, but in blockchain that's often not admissible. So there needs to be a middle term, and I would say the middle term is being sure that if the solution is more centralized, for example, you have gateways operated by virtual asset service providers, you have a way to ensure accountability. So if they misbehave or if they're hacked, you have to be sure that they can be held accountable for the damage they create. And that would be more reasonable to the end user and relatively decentralized if we can make the operations being more transparent than they are today. And I think that's ultimately going into the direction of the decentralization that we're trying to achieve with blockchain. So accountability, transparency, and assuring some security to the end users.
Right. And probably a lot of third-party audits, right?
Well, if all their procedures, if the gateways operations are all public, so imagine they have a log of operations and that's published on a public forum, public blockchain, for example, then everyone could audit the entity, right? And actually we wrote a bit about that on our paper Hermes. So in principle, they are auditable. Now, if they're accountable for the losses of their clients in a legal tender, that's different.
Yeah,
right?
well, it's harder if there's let's say a $330 million hack or something, right? So
who would pay for that? Maybe insurance. Maybe we'll have cross-chain insurers.
Yeah, we turn to jump trading or A16Z. There's a limit. Great. So anything before we break? Anything else that you want to talk about your next project or something that you're turning to in the near future that you're excited about?
Yeah, thanks for asking. I think I've covered most of it. We're quite interested at the moment in exploring cross-chain state and how can you build state out of a set of transactions, a model, so that you can know in which each part of the process you are at each moment. I think that's very useful. Visualizing that possibly it could be used as a tool for anyone that has a decentralized application and wants to have a bit more idea or control of what's happening at the moment. Also, enhancing the infrastructure for interoperability solutions, something we're doing at Block Demon and in my PhD as well. And going into that direction, helping the standardization, helping supporting tools, and hopefully helping delivering more robust solutions and infrastructure.
Excellent. So where can people find you if they want to know more about you and the work that you're doing?
Right. I don't have Twitter, contrarily to the trend. People in my area used to have Twitter. I have a personal webpage, My email is there. I also have a presence on LinkedIn, so feel free to approach me on those channels. And yeah, happy to discuss and to work on interoperability.
Excellent. Well, thanks so much for coming on the podcast.
Thanks for the invitation, Eric.